Hello everyone, today let's take a look at QB100. There's also a part C and D, but it was so big that I couldn't fit them in. So we have x and y as discrete random variables that take these values, and then we take their joint distribution to be this function right here. So we have our probability space right here. We have x, which is a random variable that takes values 1, 2, and 3, and all that means is that it partitions our probability space. So for instance, maybe something like this, and then it would assign this probability mass some value. In our case, it assigns maybe 1 here. And then in this region over here, maybe x assigns this probability mass the value of 2. And then finally in this region, maybe x assigns the value of 3. Also, key thing about random variables, there's going to be no overlap between these regions because it is a partition. So a random variable can't assign the same probability mass to two different values. So let me get rid of this shading. And now we have another random variable on the same probability space called y. And that means the exact same thing as it did for x. It's going to assign different probability masses to different values. So maybe this region right here, we'll call this y equals 1. This region here, we'll call this y equals 2. And this region down here, we'll say y equal to 3. Now we have a joint distribution, which basically just assigns the probability that both x equals some value and y equals some value to this function right here. So for instance, the probability that x equals 1 and at the same time y equals 1, that's one value that's being quantified by this joint distribution. Well, we're just going to plug in these values to our formula, and it's going to be k right here times 1 plus 2 times 1, so it's just going to be 3k. So that's the probability mass of the intersection between x equals 1 and y equals 1. So this region right here, that would be 3k. And the joint distribution is just going to do the same thing for every single possible combination of x and y. So for in here, we had 3k, but when x equals 2 and y equals 1, so this region right here, well, then we're going to get 2 plus 2 times 1, so 4 right there, k, right? 4k. Now right here, we have x equals 3 and y equals 1. So that's going to be assigned a probability mass of 3 plus 2, so 5k. And then I just filled in the rest of our boxes by plugging in the values for x and y, right? So all of these right here represent the probability masses of the box that they are in. It's not drawn to scale. Now in part A, we have to determine k so that the joint distribution is a valid PMF, and then we have to state its support. So this right here is a probability space. So for this to be a valid PMF, we have to have it such that all of these probability masses, when they sum up to 1. And since x and y are discrete random variables, we know they partition our sample space. So that means when we take the union of all of these probabilities, that's just going to be equal to the sum of them. That's just because there can't be any intersection between these two. So inclusion, exclusion, there's going to be no intersection term. So this is just equal to the sum over x and y, such that we have the probability that x equals x intersection y equal to y. So in our case, this is what it would look like, and all you have to do is sum up all of the values in all of these boxes right here, and when we do that, you're going to find that you end up getting 54k. And in order to be a valid PMF, all of these need to sum up to 1 because they are, after all, probability masses. So we set that equal to 1, and then we find that k is equal to 1 on 54. So that's our answer for part A. And then the support just means all the values that x and y can take such that the probability mass is non-zero. So it's just going to be all x and y within the set 1, 2, and 3, right? That's the support, and this is k. Now let's go down and do part B where we're doing the marginal PMF. So let's do that here. So now that we know that k is 1 on 54, we can just replace that in our joint distribution equation. And also up here in our diagram too, we can replace k as well. It's going to be on 54. So all these are going to be on 54. Okay, so now we need to find the marginal for x. So that just means the probability of all the values that x can take wrapped into one equation when we're not worried about y. So for instance, looking up here, the probability that x equals 1 is just going to be the sum of all of this mass right here. The probability that x equals 2 is going to be the sum of all of this mass, right? The probability x equals 3, the sum of all of this mass. So now in order to sum up one of these regions, we have to take the mass of each of these individual boxes where x intersects y. Okay, so we know the law of total probability. Since y is a discrete random variable, it partitions our sample space, so we can just sum up over all the possible values that y can take the intersection between x and y equals y here. So if we want this in terms of a formula, well, we know that the probability of x intersection y is just the joint distribution right here, so we can just plug this in here and then sum up over all values of y. In our case, y is going from 1 to 3, so this is the equation that we're going to solve. If I split this up, I get 1 out of 54 times the sum of y equals 1 to 3 of x, which is just going to be 3x, and then we have 1 out of 54 times 2, so I'll say 2 out of 54 times the sum over y equals 1 to 3 of y. This sum right here is going to be 3 times 4 on 2, or 6, and we multiply that by 2. We get 12 out of 54 here, and then we get 3x out of 54 here. So it's going to be 3x plus 12 on 54. We can factor out a 3. It's going to be 3 times x plus 4 on 54. We can cancel this 3 with a term in here, and we get 18. Now this is just the function for our marginal distribution for x, and we can check it, right? If x is equal to 1, then we would expect it to be the sum of these. So 3 plus 5 plus 7, that's going to be 15 out of 54. And when we plug in 1 here, we get 5 out of 18. And if we multiply that by 3, then yes, we do indeed get 15 out of 54. Now the probability that x equals 2, we would expect it to be the sum of these three right here, which is 18 out of 54. And when we plug in 2 here, we get 6 out of 18. You multiply the bottom and the top by 3, and then you get, again, 18 out of 54. And then finally, you plug in x equals 3 here, you get 7 out of 18. When you sum these up, you get 9 plus 7, which is 16, plus 5, 21. When you multiply this by 3, top and bottom, you get 21 out of 54. So these are all what we would expect. And then one more quick sanity check. When we sum up 21, 15 and 18 out of 54, then we are going to get 54 out of 54, which is 1. So all 100% probability is accounted for, so that checks out. Now let's find the marginal for y, which is going to be pretty much the same story. We want the probability that y is equal to 1. Well, it's just going to be all of this mass up here. The probability that y equals 2 will be this mass, and the probability that y equals 3 will be this mass, obviously, right? So if we fix a y, well, we know that x is a random variable, so it completely partitions our sample space. So law of total probability, we know that the probability that y is equal to some fixed y is just going to be the sum over all possible values that x can take, right, these here, of the probability that x is equal to that value intersection with y equal to that fixed value. So if we're trying to find the probability that y is equal to 3, well, we just take the probability that y is equal to 3 and x is equal to 1 at the same time, and we add the probability that y is equal to 3 and x is equal to 2 at the same time, and then we add on the probability that y is equal to 3 and x is equal to 3 at the same time, right? That's just basic law of total probability. We know this right here is going to be 1 out of 54 times x plus 2y, our joint distribution. So it's just going to be equal to 1 out of 54 times, well, when we sum this of x, well, then we get 6. And then when we add on 2 times the sum of y, well, that's going to give us 3y. So this is going to be 6y right here. So the marginal for y is just going to be 6 plus 6y divided by 54. Now let's see if that checks out. If we plug in y equals 1, well, then what do we get? We get 6 plus 6 here. We get 12 out of 54. So if we have y equal 1 here, we have 3 plus 4 plus 5. That's 7 plus 5. That's also equal to 12 out of 54. Okay, now if y is equal to 2, we have 18 out of 54 when we plug into our formula, right? And then we have right here 5 plus 6 plus 7. That's 11 plus 7. That's 18 out of 54. Now for x equals 3, y equals 3. If we plug in y equals 3 here, we have 18 plus 6. That's going to give us 24 on 54. We add 7 plus 8 plus 9. We do indeed get 24 out of 54. Now when we sum these all up, we get 24 plus 18 plus 12, which does equal 54. So this all equals 1, and it checks out again. So this right here is our marginal distribution for y. We could also bring out a 6, and we get 6 times 1 plus y, and that would factor out with the bottom, and we get 9 on the bottom. Okay, so now let's find the conditional PMF in part C for x given y. So for instance, if we're trying to find the probability that x equals 1, given that y is equal to 1, well, then we take the probability mass of y equaling 1, so we'd sum all these up, and then we'd say, okay, what's the probability that x equals 1 now that we're in our new probability space? And it would just be equal to this mass divided by the orange mass, right? We know conditional probability. So again, definition of conditional probability, this is equal to the probability of intersection between x being x and y being y divided by the marginal of y, which we'll call p sub y of y. Remember, we just calculated this in part B. It is a function that tells us the mass of when we input a given y, what is the mass of this row or this row or this row, right? And this up here is just the joint probability, which we also already calculated. It's 1 out of 54 times x plus 2y on top, and on the bottom it was 1 plus y divided by 9. Now this is just going to be equal to, obviously, we multiply this by 9, divide by 1 plus y. We can cancel this 9 on top with a 9 from the 54, and we'll get 1 on 6. Now this is just going to be equal to, right here we have x plus 2y, right, on top on 6 plus, times 1 plus y. Now we can check, does this make sense? If we're trying to take the probability that x is equal to 1, given that y is equal to 1, well, given that y is equal to 1, we have mass in here of 3 plus 4 plus 5. That's going to be 12 out of 54 on the bottom, and then we're going to have a mass of intersection right here of 3 out of 54, so this should give us 3 out of 12. Now what do we get if we plug in x equals 1 and y equals 1? Well, we get on top, we get 3, and on the bottom, we get 6 times 2, so 12, 3 on 112 as well, right? And you can check for all the others that it works as well, but this right here is going to be our conditional PMF for x given y. Okay, so now for part D, this is going to be really simple, especially since we have this drawing now. First, what's the probability that x is greater than y? So where in here is x greater than y? We already have all the probability masses nicely mapped out. So right here we have x equals 2 and y equals 1. So yes, x is greater than y right here. Okay, so now for this term in the middle, we have x equals 2 and y equals 2. So is x greater than y? No, it's not. So we are not going to include this one. Over here though, x is greater than y because x equals 3 and y equals 2. So yes, we're going to include that one. What about here when x equals 3 and y equals 1? Yes, we're going to include that. But we're not going to include any of these. So now all we have to do is just sum up these orange boxes. That's pretty simple. 5 plus 7 plus 4, that's 9 plus 7, that's 16 out of 54. Then this simplifies here to 8 on 27, so that's our answer for this part right here. Now the probability that x plus y is less than or equal to 4 is also going to be super easy. All I have to do is just sum the probability mass where x plus y is less than or equal to 4. So that's right here, 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 and here. And when I sum those up, I get 5 plus 6, 11, plus 4, 15. And then over here, I have 20, 30. So it's going to be 30 out of 54. And that is just equal to 15 out of 27. So these right here are our answers for part D. Also super simple. I don't even know why I included that as a question.